So in this video we're going to look at another oxidation reduction experiment, and this one is to prepare a solution of sodium thiosulfate and standardize it by titration against iodine. So in this experiment to start, you'll make an approximate 0.1 molar solution of sodium thiosulfate. And to make this, some sodium thiosulfate is weighed out on a clock glass, and these crystals are transferred into a beaker containing deionized water, where it's stirred to allow the crystals to dissolve, and this is then transferred into a volumetric flask and made up to whatever volume of solution the volumetric flask is for. Then we need to make our solution of iodine, and our solution of iodine is made by mixing potassium permanganate of a known concentration and excess acidified potassium iodide. So the potassium iodide is acidified using sulfuric acid. Now, the potassium iodide is in excess, and the reason it's in excess is it's needed for the reaction to go to completion, and the sulfuric acid that's added to acidify that is present in excess to ensure that there's sufficient H plus ions to allow the manganese ion to reduce from Mn plus 7 to Mn plus 2 and avoid the Mn plus 4. It's also added in excess to keep the iodine that is produced in solution. So once the iodine is made, then the titration can happen, and this iodine will be reduced to iodide ions using sodium thiosulfate. The indicator used in this titration is starch, and it's used at the very end of the experiment when your solution starts to go a straw yellow colour. Now, as you can see, I have two balanced equations here, and these two equations are very important for this experiment. The first equation is showing the permanganate ions and the iodide ions reacting in our conical flask to produce our iodine. So this is the reaction that shows the production of our iodine. This second equation here is showing that the iodine formed is reacted with sodium thiosulfate. So this is the balanced equation for the actual titration as it happens. As with our other titration experiments, it's important to know what's where in our equipment. So in our burette, we have a sodium thiosulfate solution of unknown concentration. What's pipetted into our conical flask is a solution of known concentration containing potassium permanganate and excess sulfuric acid and excess potassium iodide, which produces our iodine. Our indicator is starch, and the endpoint goes from blue-black to colourless. Now, if you were looking for the colour changes, in this experiment, the colour changes will go from a red to a straw yellow. And at the point you get your straw yellow, that's when you add your starch, and it becomes blue-black. And then you finish off your titration until the solution becomes colourless. So just a simple summary of the steps. The KMnO4 is pipetted into the conical flask, excess sulfuric acid is added, and the excess potassium iodide is added, and this leads to the production of your iodine, which is I2. This is then titrated against sodium thiosulfate. The reddish-brown colour will start to turn to a straw yellow. Once the straw yellow occurs, you add your starch indicator and a blue-black colour is obtained, and then you continue adding your thiosulfate until your endpoint occurs when the solution becomes colourless. So some sample questions that can come up in an exam question based around this experiment. Describe how you would take the reading of the KMnO4 in the pipette. So you would read from the top of the meniscus, and this is because KMnO4 is a strong dark colour. The next question is, why is it not necessary to know the precise volume of the Ki added? Another way this could be phrased is, why is the Ki needed in excess? And the answer is that the Ki is needed in excess to ensure that the amount of iodine liberated depends only on the amount of the KMnO4. So basically it supplies enough iodide ions to produce as much iodine as we need. Also, the iodide ions of the potassium iodide help to keep the I2 that's formed, or the iodine formed, in solution. The last question is, why is it not possible to make up a solution of iodine correctly? So why do you have to add the potassium permanganate, the excess sulfuric acid, and the excess potassium iodide? And that's because iodine vaporizes at room temperature, and also it does not dissolve in water. So for your calculations for this experiment, there's usually two types of calculations. The first one asks you to find the concentration of the thiosulfate when you're given the concentration of the iodine, and the second is to find the concentration of the thiosulfate when you're given the concentration of the potassium permanganate. So it is the same method for both of them. The only thing that's different is your ratio. So for the iodine, when you know the concentration, the ratio is 1:2, and when you're given the potassium permanganate concentration, the ratio is 2:10, and that is based off the balanced equations that will be given to you in the question. So let's look at an example where we're given the concentration of our iodine solution. So it says here that 33 grams of sodium thiosulfate crystals were dissolved in water and made up to 1 litre. The burette was filled with this solution. 25 centimetres cubed of a 0.05 molar iodine solution was placed in a conical flask. The titration was completed with an average titration figure of 20 centimetres cubed. The reaction between the iodine and thiosulfate is as follows. Calculate the concentration of the thiosulfate solution in moles per litre and in grams per litre of sodium thiosulfate with 5 waters attached. Now, the first thing you should notice is in this balanced equation that we have 2 moles of the thiosulfate and 1 mole of the iodine. So that's going to be our ratio. So let's now try and solve this problem. So as with all titrations, to find out the concentration of your unknown solution in moles per litre, you need to do first principles. So step 1 of first principles asks us to find the moles of our standard solution in our titer volume, and to do that you use the formula moles per litre multiplied by your titer volume, and you divide by 1000. So my standard solution that's here is the iodine, and I know it's 0.05 moles per litre. I know that the titer volume that I use is 25 centimetres cubed, and I divide that by 1000. And when I do that, I get 0.00125, and that's moles of iodine in 25 centimetres cubed. So step 2 is to find the moles of your unknown solution in your titer volume, and to do that you use your balanced equation, and we're looking at the iodine versus the thiosulfate, and we can see that it is a 1:2 ratio, but I don't have 1 mole of the iodine, I have 0.00125, so I must multiply that by 2 to find out how much of the thiosulfate I have. So I have 0.0025 moles of the thiosulfate, and that's in 20 centimetres cubed. Step 3 then is to find the molarity of your unknown solution, and to do that you do the moles from step 2, multiply that by 1000 and divide it by your titer volume. So the moles of our thiosulfate is 0.0025, and we know we've to use the moles of the thiosulfate because that's our unknown solution. So you multiply that by 1000 and you divide by the titer volume, and the titer volume is 20 centimetres cubed according to the question. So when you put that into your calculator, you get 0.125 moles per litre. So that is the answer to part A of the question. So next, if I go and do part B asks me to find it in grams per litre. So I know I'm going from moles to grams, and to do that I know I must multiply by the molecular mass. So I need to find the molecular mass of the sodium thiosulfate that's given in the question specifically. So I know that this will be 2 by 23 plus 32 plus 3 by 16 plus 5 by the molecular mass of water is 18. And when you put that into the calculator, you get 248. So I know I need to do the 0.125, and I need to multiply that by 248, and that gives me 31 grams per litre. So that is the answer to part B of this question. So let's try another example now, but this time you're given the concentration of your potassium permanganate. So this question says 25 centimeters cubed of 0.02 molar KMnO4 is added to excess potassium iodide and dilute sulfuric acid to make an iodine solution. This solution is titrated against a sodium thiosulfate solution of unknown concentration. The average titration figure is 18.7 centimeters cubed, and the reactions involved are as stated. Calculate the concentration of the thiosulfate solution in moles per litre and grams per litre. So this is the exact same process as the last example, except the only difference here is your ratio will be different. So when you're asked to do or to find the concentration of something in moles per litre in a titration, you use first principles. So the first step of first principles is to find the moles of your standard solution in your titer volume. And to do this, you use the formula moles per litre multiplied by your titer volume, and you divide that by 1000. So the moles per litre of our standard solution, which is the KMnO4, is 0.02, multiplied by the titer volume, which is 25 centimeters cubed, and divide that by 1000. And that gives you 0.0005 moles of KMnO4 in 25 centimeters cubed. Step 2 is to look at our ratios. So from the balanced equation, I can see that 2 manganese react to produce 5 molecules of the iodine, and then we can see that every 1 iodine reacts with 2 of your thiosulfate. So if 1 iodine reacts with 2 of your thiosulfate and we have 5 iodines, that would mean that we actually end up with 10 thiosulfates. So our ratio of MnO4 is to thiosulfate would actually work out to be a 2 is to 10. And the reason that it will be 2 is to 10, just to explain to you again, is 2 of the manganese reacts to give 5 iodines. And for every 1 of these iodines that's produced, we need 2 of our thiosulfates. But we don't have 1 of the iodines, we've produced 5 of them, so that must mean we must have 5 times as much thiosulfate, so that would give us 10. So the ratio is 2 for the manganese is to 10 for your thiosulfate. Now, I don't have 2 moles of the manganese, I actually have 0.0005, so that would give me 0.0025 moles of the thiosulfate. So that means there's 0.0025 moles present in the 18.7 centimeters cubed of the thiosulfate. So step 3 asks us then to find the molarity of your unknown solution, and to do that you use the formula of moles multiplied by 1000 and you divide by the titra volume. So the number of moles of the thiosulfate that we have present is 0.0025. That gets multiplied by 1000 and you divide by the titra volume, which is 18.7. So if we do that, we get an answer of 0.1337 moles per litre. So that is the answer to part A of this question. Now, if we go and do part B, they want the answer in grams per litre. So to go from moles to grams, you must multiply by the molecular mass. So we need to go and find the molecular mass of our sodium thiosulfate. And we and I need to multiply that by 248, and that gives me an answer of 33.158 grams per litre of the thiosulfate, and that is the answer to part B. That's it for this video. Have a read over the learning intention to make sure you understand everything